Hello, everyone. Good to see so many eager people ready to go. I will, of course, be waiting a few minutes to the 5 minutes past for the Latrobe policy, starting 5 minutes past. But in the meantime, feel free to ask me any questions you have that you want to quickly get some answers for.
I've got some questions on the assessment.
Sure, Matthew. What's up?
First one is there's no preference for the referencing style, is there?
There's no preference, no.
Okay, all
You're
right.
not really assessed on the referencing.
Okay, all
Yeah.
right. The second thing about the referencing was
Hmm.
in the assessment description, it like for the second part where you add more photos, I just downloaded all the photos, not just for my two that I selected, but for the tomato, apple, and banana.
For all of the extra images, yeah.
Yeah,
Yep,
yeah.
that's right.
I,
Yeah.
I guess I'd have to reference those as well, wouldn't I? The apple, banana.
Uh, I mean, if you're getting it from a source, maybe give a reference, like if it's Pexels, then just say you get it from Pexels. We're not we're not expecting you to go reading papers. We're not expecting too much on the referencing. It's just if you've got it from somewhere, make sure you let us know where you got it from. We don't care about style on it at all.
Okay. Um, One last thing, and maybe you can't answer this because it gives away too much, but
I'll let you know.
yeah, let me know. When we're doing the epochs um,
Hmm.
train, obviously because we don't have many examples, I'm tending to find that the training set will hit 100%,
Hmm.
but um, the validation or the test set is still improving with each um, epoch. Uh,
Okay.
so I was kind of using my measure as when the loss was no longer going down, rather than cutting. Because I mean, normally you would probably
Yeah.
well, first of all, you probably don't want to hit 100% on your training, but even if you did, you would normally be overfitting. That's all.
Uh, all you, c- in fact, all you care about when you're training your own models is how well it does on the test set. How well it
Yeah.
does in the training set is almost entirely irrelevant to anyone else. So the only thing you care about is does it do well on the validation or test set, whichever one you're aiming to do well on. So that seems reasonable. That yes, you want that loss curve to look good, and a
Yeah.
good loss curve is when you get that saturation of the loss, and that's what you should aim to get, even if the accuracy on the validation or the training get to 100%. You should still aim for that nice curve on the loss curve.
Yeah. Yeah. Oh, great. That's what I've done. Excellent.
Yeah,
Okay.
good.
All right. Thanks.
No problem. That's good.
Um, that's one. I want to ask a question about the batch size. Are we also allowed to modify the batch size?
The batch size. Uh, Theoretically, yes. It wasn't one of the options we intended for you to try, but if you want to, you can. The only thing is that you can't get it very large because
Yeah.
well, I suppose it depends how many images you've collected. If you collect hundreds of images, then it would make sense to
Mhm.
use the batch size. Yes.
Okay. Thank you.
Yeah.
Hey Brendan, Shruti here.
Hi, Shruti. How are
Yeah,
you?
hi. So with regards to having additional training images, is that fine if we adjust the contrast, brightness, everything of the images we have collected, just so that we get more images for the training set?
Uh, yes, but only if you've otherwise already satisfied the amount of images. So the images that you need to take, like 15 that you need to take with your own camera, you cannot
Yeah.
do that for. But
I
for
have.
the extra images, that we have the next part down below that, where we're talking about getting extra images, that's perfectly fine for you to do it for extra images to make those variations. Yes.
That's right. Yeah, it's for the extra images. So I have collected
Yep.
the initial 20 images.
Yep.
So just for the extras thought, yeah,
Yep.
to do something like
Exactly.
that.
Yeah.
Yeah. Thank you.
Good question.
Oh, uh, just want to ask about the relation with assignment one. What is
Okay.
saying that we will be using the sample image of assignment one and replace the one on assignment two, and then do the actual classification again. That's the way it is.
So for assessment two, you must
Yeah,
be
assessment
using,
two.
yeah, your assessment two,
You're
you
using the
must be
same.
using the images that you used for assessment one
Yes,
as your
the same.
test set.
Yeah, okay, good. That's right. Yeah,
So whatever you had for assessment one, that's your test set for assessment two.
yeah, but you're only using the two new class, not the three class. You know, the apple, banana, and tomato. Are you still
You
using
need
the same?
you need to use all of them. You're training a
Oh,
model to be good at all of them. You have been
okay.
given new images in assessment two for those other classes.
Yes, yes, yes.
So
So
you,
exactly whatever you use on assignment one, the 25 set, you
mhm.
use that one on assignment two, right? Yeah.
Yes, yes.
Okay.
All of the images you use in assignment one, you're using in assignment two.
Okay.
That's right.
Thank you very much.
All right.
Brendan, I just had
Sorry.
a
We're going to start the lecture. If you have a question, you can put it in the chat. Um, I will answer it later. We really have to get to the lecture. There's a lot to cover in this one. So we're going to get started now with it. So I'm sharing my screen. Would someone be able to tell me if they can see my screen?
Yes. Yes.
Excellent, thank you. And I want to try. No, that's not going to work. Okay. Yep, cool. All right, so welcome to Lecture 7, Module 4 of in Artificial Intelligence Fundamentals. Today we're going to be talking about the sort of more modern generative AI algorithms. In particular, we're going to go deep into LLMs. We're going to be talking about how LLMs can read words, how we take those words, we turn them into numbers, do some numbery calculations with an LLM, and then get words out the other side. And we're going to talk about first just that basic level text into text, yes, text to word embedding. So we're going to go text into numbers. Word embedding is a kind of number, and you'll see what that means as we go through. So text into numbers into text. So one word into number into one word. And that's going to be the first part, just that simple thing. Then we're going to talk about how we can use that one word in, one word out in a method to generate sequences. Because when you type a message to ChatGPT, it's a whole sequence of words, and then it responds with a whole sequence of words. So we also need to talk about how those sequences are made. And then the third thing we're going to talk about is the training procedure for those modern LLMs, how they get those capabilities and what kinds of data are they being trained on. So by the end of this lecture, lecture number 7, you should be able to explain how text is represented, as in turned into numbers, for language models through the ideas of tokenization and word embeddings, or sometimes we just call them embeddings or embedding vectors. So you should know by the end of this what those two ideas are and roughly how they work. Then you should be able to explain how an LLM can process a sequence of tokens, which is the result of tokenization, tokenization, process a sequence of tokens, and how that becomes text. Okay, how that becomes a sentence that it will respond with. So let's get started. So we're going to start with talking about the idea of, what is a text-based model? A text-based model is just a model that's going to accept text and it's going to respond with text. And it's at the moment it's just kind of a black box, and we're going to peer inside and see what that black box it consists of. So we know that machine learning models can only really be run with numbers. We can only put numbers in, do some mathematical operations, get some numbers out. So the first thing we have to talk about is this outer layer of how do we turn text into numbers and then back from numbers back into text? Well, let's take a step back and talk about how computers already do that, because computers run on numbers and we have a bunch of text on screen, and yet we're able to transmit that text around to different places. I can send a text message to my friend and they'll get that text message and it'll be text for them, and we don't lose any of the characters along the way, usually. So how do computers already represent text? Well, we talked about this at the beginning. Well, let's refresh ourselves on exactly what happens. Each of the characters are assigned a unique numerical ID, and every string in a computer, every string of characters in a computer is behind the scenes turning all of the characters into these numbers, transmitting the numbers, and then when it comes time to display it again, it's just turning it back, it's just doing the opposite direction. So when we take characters and we turn them into these numerical values, this process is called encoding. It encodes the text into a number. And so the opposite way is decoding, taking the numbers and turning them back into readable human text. And what we can see here is actually called a common encoding scheme so that everyone knows what you're talking about. If you get these bytes, you know what they map, which characters they map to, because everyone uses the same mapping system. They all use ASCII. So ASCII is just an encoding scheme that just says capital H is this number, lowercase e is this number, and everyone knows, all right, if I see this number, it means capital H. If I see this number, it means lowercase e. And so that means that each letter always just has a corresponding number to go along with it. But we have to ask the question for a computer, not for a computer, for LLMs, we might want to do this differently, because all of the characters being turned into numbers, well, each character doesn't really have any meaning. So it would be nice if instead of encoding character by character, we could somehow have a single unit of meaning instead of, like, this is just one character and it's another character. We could theoretically do character-wise, and some people have done experiments with language models using character by character, and it does work, but it is better if we can have sort of larger chunks. Okay, so can it be done differently? And it should be done differently. Instead of doing it character by character, instead we can break the text up into larger chunks of text, and then we can give each one of those chunks a unique numerical ID. So that means that if we're talking about this system, encoding would be replacing a chunk of characters with a numerical ID, and then decoding would be replacing the numerical ID replacing it back with a chunk of characters. This would be nice because then we can have maybe groups of characters that mean something, such as words, right? So if we wanted to tokenize this text, we might first think, let's just break it up into the words, and then the words can go in, those are numbers, and then the numbers can go into the model, and then we can, when whatever the model responds with, we can detokenize it, we can turn it back into text. So tokenization is the same as encoding, and detokenization is the same as decoding. We use the same words. You can use whatever word you like. It's just encoding and decoding comes from normal computing, and tokenization and detokenization comes from machine learning side. So the text chunks that we break it up into, they're called tokens. And for now, we're just going to think about them as words, and we'll talk about what we actually do. It's slightly different, but for now, we just think about them as words. So we can think that we're going to break this hello friend up into some tokens, and it's going to be hello is 10,425, comma is 48, and friend is 10,198. And then model does its magic, spits out some numbers, and those numbers are 1,498, and that turns out to be the word hi, and then the word there, and then exclamation mark, and then a smiley face, right? So there's a few different ways that we could choose to tokenize text. As I said, the simplest way is words, because or the simplest way that gives us meaning per token is to do it by word. So let's have a look at what that looks like in a bit more detail. Okay, so we have character tokens, right? This is what ASCII and Unicode do. We could do that, and we could call that tokenization and decode tokenization, the same as the encode and decode. But as I said, we want the tokens to be signifying ideas, such as words. Single characters have very little meaning by themselves, but if we can use words, then the model's going to be sort of thinking in terms of words rather than having to learn how to compose characters into words, right? So we want to break up the text into word level tokens. We have the sentence, "Hello, my friendly friend, Dr. Jekyll." Uh, we would be converting the word hello, a comma, my friendly friend, comma, Dr. Jekyll. Each of these, in my system of these word tokens, each of these are distinct tokens with their own numerical ID. And so tokenization is just turning it into these numbers, and detokenization is just turning it into those numbers. And then you just have a big list of all of the possible words in the English language, and you have a mapping where each word is given a unique ID, and that unique ID is just for only for that one word. And so you can perfectly translate between word and numbers. However, this idea, this like breaking it up into word level tokens. Sorry, I just want to double check on the chat. Yep. But word level tokens. There is a couple of not great parts about this. Something that doesn't quite work, doesn't quite make sense, and is a bit awkward. Um, Consider the words build, builds, and building. So we've got a question. Should each of those be different tokens, or should they be like similar tokens somehow? Because they're all kind of the same meaning, right? So we kind of would want to have something that means build and then maybe an additional part that says, okay, build, but it's builds with the S on the end. And so you can split up to two tokens. That would allow the model to know that builds, building, and build are all the same thing. But then you've got the modification to form a proper English sentence, right? He was building his building, right? It wouldn't make sense that he was build his build. We wouldn't want to like ruin the language, right? So if we break that up into one part is build and then we have the ending, this is a kind of simple subword token, right? It's a it's a subword because it's friendly is broken up into friend and ly, so you have subword tokens. And so we have sort of better situation now where you can look at the sentence again. Hello, my friendly friend, Dr. Jekyll. Um, and hello is translated and comma is translated and my is translated and you see comma, comma, they're both 48 because it's the same word. It has to be the right unique identifier. But now also friend of the friendly and friend, just the word friend by itself, they're both the same token as well. And then that tells the model that we've got friend and then a modifier on friend, right? And then the model can internalize that and learn that. And that's maybe a bit better for the model so that it can understand what's going on. However, that's not the only problem. There's some others like doctor dot. Should it be doctor with the dot included or not with the dot included? Sometimes people don't put the dot in. So does that mean that the doctor without the dot is a different token to doctor with the dot? Um, and then another one is consider the words football and footprint. Kind of have the same base word, but kind of not. They're different. They're pretty different ideas. How do you handle misspellings of words? What if it's the same word, but it's just misspelled, like two characters are swapped, receive spelt the wrong way, you know? So identifying all of the different word variations would be pretty much impossible. It would be there's too many different variations. It ends up being subjective as well, and then different people have different opinions about how maybe it should be done. And so what we want is some way to automatically perform this subword tokenization, right? We want to figure out how to do this subword tokenization without having to define it ourselves. And so there's a algorithm that came up just in the just before LLMs uh, took off. This is part of what allowed them to work. Was an automatic automated subword tokenization scheme. And this is the default tokenization algorithm used by most LLMs. Pretty much all LLMs will be doing it. I don't think any LLMs don't use this. And the way it works is that we analyze a large collection of training data and it creates a vocabulary of commonly occurring subword patterns. The algorithm is in detail in the subject notes. I'm not going to go into it in too much detail here. I'm just going to talk about it because I don't want to get distracted too much with that because there's a lot to cover. But here's the basic idea of how it works. You start with just all of the characters, and then you scan through and you find which pair of those was the most common in your training data. And then the most common pair of tokens becomes a new token. You add that to your list of tokens. So now it's A, B, C, D, or whatever, all of the characters. And then you have maybe the letters T, O. Maybe that's the most common pair of letters. That's a new token, TO. And then you do it again and you find TO with A, TO with B, right? In different ways. And you find what the most common sub word pattern is. And you just repeat this. You repeatedly build up tokens by how commonly occurring they are until you've hit a sort of word limit. And maybe that's 40,000, maybe that's 200,000. And different LLMs will have different number of words. They'll have run the same algorithm, but they'll have different number of words that they're targeting. So it'll be a different encoding. But you end up with a few nice properties with this, which is that in the best case, it's like word tokenization. It just has each word as a separate token, and you can just express the sentences with just words where each word is a concept. But it also automatically handles misspellings, variations on the spelling, to create other tokens where necessary to create those. And it also, the thing is that it means that if you have very rare words that have very weird spelling, somebody's name that's never seen before, somebody's special name, it's just their name, um, it breaks it down into character, it goes down to character by character again. So there's sort of this like middle ground that is word embeddings, sorry, word tokens, where it can, and character tokens where it needs to, right? And it can do this automatically, very smoothly transitioning between them. So all LLMs use this byte pair encoding, right? And then that means we can turn any text into a sequence of unique IDs, and then those unique IDs can be transferred back into language, and it's a one-to-one mapping perfectly. We can tokenize any text, right, into these IDs and do that backwards and forwards. So are we done? We've got the text being turned into numbers. Hold on, give me a second. I need to. So we've got text being turned into numbers. That's what we needed, right? Can we just feed those tokens into an LLM and call it a day? Well, no, we can't. There are some problems. So let's assume after we've done byte pair encoding, BPE, byte pair encoding, we get the following tokens for the different words. So dog is 3385, cat is 4147, and surprise is 3721. If we just feed these token IDs into the model as is, then this tells the model something a bit weird, right? These are numbers on a 1D number line. And it would mean that surprise is somewhere between dog and cat. That's not a good property for words. And it would also mean that dog plus 336, which is another word in this system, equals surprise. And that's also not a great property for words to have. So we need to be able to express them in numbers in a way that the computer knows how to compare numbers, and it doesn't have these weird properties of adding these two means another one, right? So what we need is we need text coming in, being tokenized into a number. We need something else that goes into the model and takes a word and predicts the next word. And the next word comes out as a number and we can detokenize. And all of that makes sense. We've got the tokenization and detokenization that we've just been talking about. We've talked about how to train a model. We just need something here to express the words better, to express them in a way that the model can understand meaning in a sense for the words.
Brandon, sorry. Just
Yes.
just one question. You know, that's previous slide, and it was also explained in the module.
Mm-hmm.
It doesn't make sense. I think I read it a couple of times, and again just now when I try to listen, like
Mm-hmm.
why are you pairing dog, cat, and surprise?
So these are three, this is hypothetical, but we're kind of picking three random words from the words that were found in byte pair encoding. And so byte pair encoding has a bunch of word tokens. You're comfortable with words
It,
going to tokens? That's all good?
yeah, yep,
Yep.
yep, yep,
Cool. So if we feed in the token ID as is,
yep.
we're telling it, okay, dog is number 3385. The model just goes, okay, 3385. Cool. That's the input. And then we feed in another token and it goes 3,721 for surprise. Okay?
Mm,
So if these token IDs mean those words and then we just give those token IDs to the model, these words are on a 1D number line. Let me draw.
what is some 1D line means?
It just means, we have a number line, so we have 0 over here and we have 10,000 over here. You can see what I'm drawing?
Yeah, yeah, yep, yep.
Yep. Yeah, it means that um, the model is going to interpret this as a number line.
Mm,
So dog is going to be maybe here,
mm-hmm.
and then surprise is here, and then cat is here. So the model is going to say, okay, cool. These are different numbers, which means that if I was to add a little bit from this word, I would get that word.
Yeah.
That's how the model would understand these numbers.
Oh, okay. Yep. They just put it in order. So that's how the
Because they're just in order, because
oh,
that's if we just give the ID, they are ordered on the number line.
yeah, okay.
Yeah. It's a good
Okay.
question.
Yeah, yeah, thank you.
Okay, cool. So we need to do something else. They can't be ordered like that. They have to be ordered in a different way. We have to relate them to one another, but not through just the through that order, because there's no such thing as that order. Oh, hold on. How do I get rid of this? Um, right. So how do we do that? What we do is replace each token ID with an embedding vector. So an embedding vector is just a vector where a vector is just a list of numbers. It's just maybe 1,000 numbers. So instead of it being one number, we replace it with something that's 1,000 numbers. Okay. And whatever the exact value of that vector is, that's what we're going to use to identify the word. Now, this seems like a really complex, difficult idea, but we've actually been kind of setting this up pretty much the whole time. We've seen all of the pieces of this, and so I'm going to go back now to previous ideas that we've discussed to explain how this works in terms that we've already looked at. So we're going to start with one-hot encoding or one-hot embedding. This is similar, but not quite what we have done what we're going to do, but it shows the general process. So previously we did one-hot encoding for suburbs in our house price data. We said, okay, we have the same problem. We can't order these. These shouldn't be ordered, so we need to have more dimensions here. So what we did was we replaced the word Oakview with the one-hot encoding or one-hot embedding 0, 1, 0, 0. And we did that for every row. And so for each suburb, we created a one-hot embedding vector like this. The word Brookville became 1, 0, 0, 0. The word Oakview became 0, 1, 0, 0, etc. So first thought is like, maybe we can just use this. Maybe we can just do this. This solves that problem of the ordering being a problem. We give each word its own dimension. So Brookville gets that dimension, Oakville gets that dimension, and then we have a one hot embedding vector for each word that looks like this. Can we just do that? And the answer is no. There are two big problems with that. When we're looking at the suburbs, we had 4 suburbs. So that meant that one hot embedding created a 4D vector, which means that if we had 100 unique tokens or 100 words, that would be a 100D vector. But the human language, BPE, we're talking 40,000 to 100,000 unique tokens. We can't really, like, that gets too big. 10,000 dimensional vector is too big. 100,000 dimensional vector is too big. It's too wide. It would be too much to compute. It wouldn't make sense. And the second part of that doesn't work super well is the fact that we have a 1 and then a bunch of zeros. It's a very sparse description, and it also means that each of the words have a very they are the same distance apart from one another. They have the same difference between the words. But we of course know that words don't have that in reality. Some words are more similar than others. So while one-hot encoding does not imply relationships, so it doesn't have that 1D implication, we do actually want to have some kind of relationship between the tokens, which one-hot encoding doesn't actually give us. So if we look over here, the distance, if we have the 0, 1, 0, 0, 0, just like with just a bunch of zeros and a 1, bunch of zeros and a 1, bunch of zeros and a 1, the distance between cat and surprise is 1.41. I'll leave you to figure out why. We can talk about it at another point, why it's 1.41 instead of 1. And distance from cat to dog is also 1.41. But cat and dog are kind of more similar words, so we would hope for our embedding to capture that information a bit better. So what we do instead is we create a vector space embedding. Instead of having 100,000 dimensions, in this example, we have only 3 dimensions, but we use those 3 dimensions to place the words such that distances make sense. So in this case, if cat was 0.89 and 0.74 and 0.24, and it was one vector that had these 3 numbers, and that was the vector we used to represent the cat, represent the word cat, and dog similarly, and surprise similarly, we could measure distance with this vector space embedding by doing distance in 3 dimensions, right? This is just distance in 3 dimensions, that's all. Okay? But of course, that begs the question, how the heck do we make these? How do we make this vector space embedding? So we can solve those problems by making a good vector space, and what we want from the vector space is each word, each instance is a point, and the relationship between those points is describing the similarity and is calculated by the distance, which means that closer words are more similar and words that are further apart are more different. This is what we want to get to. So how do we make it? We want to be able to measure how similar they are, right? So the vector space has to represent it. So maybe we think about measuring it, right? And we've seen this idea before about measurements becoming points in space that tell us about relationships between things. Way back in the first 2 lectures, we had this example where we said taking a person, we could take 2 measurements from a person, and then if we have 2 measurements, that would form a point in a 2-dimensional space. And then we can say, once we've done that, there's this implicit structure that sort of appears here where people who have similar height and weight are more similar than people who have a different height and weight. And we can see that graphically, and we can conceive of it as a distance, right? These are closer, those are further away. We kind of want the same thing for words, but instead of it being in 2 dimensions, maybe it'll be in many more dimensions. And we've talked about how these vector spaces can be in many more dimensions. If we have a table that has 100 rows, then it's a point, each row is a point in a 100-dimensional space. So we might want to be able to measure things from words. Maybe we want to measure 100 different things about words so that we can get a nice big vector space, or not too big, but not too small for the vector space. And with maybe 100 to 1,000 is a sort of middle ground that we would look for. So similar to how we just looked at humans and we thought of abstracting humans by measuring weight and height, and that becomes a point in space, in 2D space, we can think about abstracting words by measuring properties, or we also call them features of words. And then those measurements, those properties, those features, they will become columns in our big collection of words. So each row is a word, each column is a property. Okay, so we can imagine doing this. We could ask, is it a noun? Is it a verb? Is it an adjective? Is it an adverb? And we can have that as part of it. We can say, what's the length of the word? We can say, what genre of fiction is this word most used in? We could think of 1,000 different ways of being able to measure things about the words, but that's also very hard. As we have talked about before, when something gets really hard, we want to be able to do it automatically. Previously, in this lecture, we've talked about byte pair encoding. That was an automatic way of doing something. But for this, vector spaces, it doesn't seem clear how we could make an automatic way to place them so that they're similar. There's certainly no easy way. We've talked about features before, though. In particular, we have talked about visual features before. And so the process of automatically creating a vector space for words is actually very similar to the process of automatically identifying visual features. So let's recap on that one. Automatically discovering visual features. When we talked about this, we talked about how previously there was a bunch of hand-engineered features, and then eventually we figured out we could just use the algorithm, the neural network, to discover those visual features for us. And we can say that neural networks can automatically find features from image data just by pixels to class. So we want to see, like, can we do the same thing for words and tokens? The answer is yes, absolutely. This is how we do it. We basically give each word an embedding, and we ask the model to move the words in the space so that the words that are similar are put together, and that words that are more dissimilar are pushed further apart. And we'll talk more about how exactly that works when we start talking about how the models are trained, which is at the end of this lecture. But the point is that it is learned embeddings to put those words into an embedding space such that it has that property. Similar words close, dissimilar words are far apart. I'll keep saying it because that's the most important part, right? Similar words are close, dissimilar words are far apart. So now we have the answer to what goes between the number and the model. We have this embedding process. So what we do is every single word, all 10,000, all 40,000, all 100,000 words, however many words we have, how many tokens we came up with byte pair encoding, however many tokens there are, each one gets its own embedding, which might be 3 columns, it might be 5 columns, it might be 1,000 columns. Usually it gets closer to 1,000. And each word then is a row in that information, that embedding, which we can think of in the same way. I'm just going to go back a bit. In the same way that if we have this table of height and weight, of these properties that go to a two-dimensional space, if we have these embeddings, which is kind of like a table where each row, we don't know what the columns are, right? Just to be clear. Same as with the image models, we don't tell it which visual features to pay attention to. And for the words, we don't tell it what properties to extract about the words, but it learns how to do it, and it has several slots, several columns to put information into. And so each word becomes a vector, and that vector is a point in high dimensional space. If there's 3 columns, there are 3 dimensions to the space. If there are 1,000 columns, there are 1,000 dimensions to that space. But in either case, the word is a point in that space. And remember, again, the idea is in that space, words that are similar are close together, like we have this cat and dog are close together, and dissimilar words are far apart. Cat is further away from surprise than it is from dog, same with dog and cat. Of course, this is in high dimensional space, so it sometimes becomes difficult to visualize, but that's the idea. The distance between those points in those high dimensional space tells the model already, before it doesn't even does any processing of what that means, it already has an idea of what similar words like when they're similar words, because it also means that the model doesn't have to work very hard to process similar words. They are similar ideas. They have similar numbers inside of them. That's really useful for the model. Okay. I'm just going to check the chat. This is the end of that. We've up to this point, we've talked about how we turn one word into another word. So we take a word and the model predicts what the next word is. So if we say hello, the model might say hi. The next section, we're going to talk about how we can use that to produce sequences. I'm just going to have a look at the chat to see what people are saying. So foreign languages is an interesting point. When byte pair encoding is being run, it makes no distinction what language. So there's tokens, subtokens in there for English, Chinese, Italian, French, uh, Japanese, whatever. There's a bunch of different tokens, and there was actually a problem that a lot of them are very English focused. So most of the tokens are based on English because most of the text that it was using was English, but there's been some efforts to specifically include other languages since then. So byte pair encoding has been improved in that way. And so each individual letter and number has a vector, but so does all of the combinations of letters that are found. Okay, so now let's talk about sequences and generating sequences. This lecture is probably going to go a little bit over. I hope that's okay. I think this is very important, so I'm going to make sure we give the time. So we're talking about sequences of text, sequences of words. From here on, I'm just going to use token and word interchangeably, even though technically it can be subwords. It's just easier to talk about words, so we're just going to use words to talk about the theory. So we have a sequence of words, which will be a sequence of tokens. Which word do you expect to hear next? Roof, chair, mat, happiness. See, Siva says mat. Mat is a good guess. I think chair is a pretty good guess. Cat sat on the roof. Yeah, sometimes. Depends if it's an outdoor cat. There's sometimes cats are on roofs. The cat sat on the happiness, however, absolutely not. That doesn't make any sense, right? So what we can think about is that each of these words almost has a probability of being the next word, right? Mat might be the most likely, followed by chair. Roof would be a reasonable probability, and then happiness would have almost no chance. We would never see that, right? We would never see the cat sat on the happiness. That would never be an English sentence. So we're going to talk about how we get a model to do that. But in order to get there, we actually need to simplify our diagram. So we've ended up with a fairly complicated diagram where hello comes in, gets tokenized, becomes embedded, goes into a multi-layer network, and then that comes out as a number which gets detokenized into hi. We're going to simplify this and just skip some steps when we're talking about it, just so that we can see what's going on. It's all still happening, but we're we're visualizing it a bit differently. So we're going to have just the word, we're going to have the embedding of the word, we're going to have an arrow through some layers, and then we're going to have the output word. But it's still doing the tokenization and detokenization and embedding and all of that. Okay. So now we're going to talk about an LLM, and this is what an LLM looks like. Okay. You have a word coming in, you have embeddings for that word, and those go through layers of computation, and you have a sequence of words where they're sort of connected across time steps. And then at the end of the sequence of words, the model produces a probability distribution over other tokens. So we're just going to use words here, but it's just over tokens, right? And so if we put in the sentence, hello, friend, hello, comma, friend, full stop, the next word most likely is going to be like hello, hi, greetings, right? And the model might think hi is the most probable next word, and then followed by hello and greetings. And so for now, we're just going to assume that in order to produce the output sequence, we just choose whatever word is most likely. So in this case, we'll choose the word hi, and we won't even consider hello because it's not as likely as hi. So that's what we're going to do, and then we're going to talk later about sort of doing it a bit more in a bit more fancy way using these probabilities. But for now, just assume it's the most likely, and we're going to generate sequences like that. LLMs are what's called autoregressive. In order to produce an output sequence, what you do is you put the whole input sequence in, you take the first output, and then you take that back and you put that in as another token and then run the whole thing again. Get another word, get the output, run it all again. This is called autoregressive. Auto meaning self, basically. This might seem a bit expensive because you need to redo all of these, but actually, if you look closely, a lot of the calculations can be cached across runs. So it can just be, you only need to do some of the new steps, the new connections that would be made. But this is the basic idea of producing an output sequence. You have some input sequence, you start producing the output sequence, and then you start feeding in the output sequence as the next steps. So you might have heard of LLMs as being fancy autocomplete. This is why. It's because the model is just predicting the next word, predicting the next word, predicting the next word, and predicting the next word. And you can think of an LLM as just being a function that takes in a sequence of words and predicts one other word. And the way that we construct an output sequence is actually sort of outside of the model. We just run code on it. We just do a loop over it. We just use code to run the model, run the model, run the model, run the model a bunch of times to get the final output sequence. Okay. So this is the basic idea of generating sequences. Let's zoom in a little bit and talk about some of the layers. I think it's important for you to know about these layers. What's going on in these connections? What's going on is something called a transformer block. These were a major innovation and part of why LLMs can work so well. And they consist of two kinds of operations. They have a linear layer, which is something we've kind of been seeing the whole time, and it has an attention layer, which is something we haven't been seeing exactly. So the linear layer is what happens between these bubbles in this diagram. We've seen this diagram before. We haven't really talked about it too much, but hopefully the basic idea, it makes sense. You have a certain amount of inputs, a certain number of outputs for each layer. This is a layer that has 3 inputs and 5 outputs. This is a linear layer. It has a combination, every possible combination of dot to dot is covered, and each one of those is a parameter. So this first layer, this layer 1, has 15 parameters, 3 times 5 parameters. And so if you have a neural network, there's a bunch of layers, a bunch of linear layers, it's just this. This is just what it looks like. And we've sort of seen this before, seen this throughout the subject. Attention layers are a little bit different. They are used in conjunction with the linear layer to collect information from a sequence of data. And so remember that each one of these rectangles is a layer, and the output of the layer is being considered for this new layer. So we're talking about the input for this layer. We're going to combine together the outputs of all of these other layers, right? And actually, in the diagram, it's important to know that this layer, can you see my cursor, by the way? Maybe I'll just,
Yes, we can.
yeah, okay, cool. I'll still use the spotlight here for this one. This layer here and this layer here, they have the same parameters. It's just we're using them with different inputs, okay? So horizontally, they have the same parameters, but vertically, they're different parameters. So this is the first layer at time step 1, the first layer at time step 2, first layer at time step 3, and this second layer is taking the input at different times, and it's combining them together using what's called attention. Attention is a process that calculates how important each of the previous inputs at different time steps are. And that's what we're seeing sort of at this junction point above each input. It's finding how important each one is, and then it's mixing together the information based on how important it is and using that as the input to this layer. So important words have a high score, not important words or tokens have a low score. So in this case, hello is very important. You finish the sentence, hello is the most important, so it's probably thinking, what do we say back? Is it hello or hi, right? That's the attention layer. So these diagrams are made up of those. We should know, basically, all I want you to know from this is that transformers are made up of linear layers and attention layers. That's it. That's all they do. Next, just a small side bit we should talk about is context windows. I mentioned that it's maybe not too expensive to run these things repeatedly, but it can get big and expensive if it gets too big. If the information gets very long, if you have put in a whole book, for example, it would need to process the whole book before it can respond. That's almost too much. So for LLMs, usually we have a fixed size on how big how many tokens will be in history. And we call this the context window. You can think of this as if you're talking to someone and you go backwards or forwards, the context window is just the information that has come up in the conversation so far that you're referencing within the conversation. So in this diagram, if we say the context window size is 4, which is way too small, usually we're talking like 10,000, 100,000 tokens. For the context size, but in this case it's 4. The model just sort of cuts off everything else. And this allows us to sort of control the processing time and memory footprint of the model. And we'll talk about that more in the next lecture about choosing that value. But the important part is just if it's outside of the context window, it cannot influence the model. It simply cannot influence it because the only things that cause this output to be the way that it is are the things that are connected together by these attention connections, which is being cut off by being outside of the context. Okay. And the last thing we're going to talk about is control tokens. So we've just now set up a scenario in which an LLM is sequence in, sequence out, and that's all an LLM is. And that's true. That is what an LLM is. It is just sequence in, sequence out. Just a series of sequence of tokens in, a sequence of tokens out. But we know that LLMs can do more than just respond with text. They can write and then run code. They can trigger tool calls. They can send emails if you set them up in the right way. So how is it that they can do that? Well, the way that all of that is handled is through control tokens, right? Control tokens are included in everything you send to a LLM, and it sort of guides the LLM to understand what's happening. And it is a way for it. One of the things it does, which is really important, is it differentiates between what you have said and what it has said. So it'll have something like, if you're looking here on what the LLM sees, if we have a message saying, hello, friend, and we're sending it to ChatGPT, and it responds with, hey there, what's on your mind today? What is actually seen by the LLM is first, it has a special token that it knows means, all right, this is the start of what the user is saying, start of the user prompt. And then it has the token for hello, comma, friend, dot, and then it has another token that say, okay, that's the end of what the user has said. Now I'm going to start responding. And then it starts responding with, hey there, what's on your mind today, and has a sequence, and then it has to have another token that says, okay, now I'm finished generating. Send that off to the user, right? We're going to send that message to the user. This is the token that says that. We're going to end the special token that says end of the assistant. That's saying it's the end. And so the LLM has to learn how to use these tokens appropriately. And it learns how to do this through its own training. We actually have to explicitly train it. All right, there's this token, and you use this token in this way, and here's how you can use it. And we'll talk about exactly how models are trained in now, right now, in a moment, which is right now. So we're going to briefly talk about the 3 stages of training an LLM. How do we get the LLM to know how to respond to a human appropriately? Okay. There are 3 main phases which we're going to quickly go through. Okay. We know that LLMs, hopefully we've covered it. We know that LLMs need to be trained on truly massive amounts of data to be able to be good at all the things they need to be good at. And even with all of the data we have, sometimes LLMs, as you've seen in the labs, they can be good and they can be bad. And they're still LLMs, but they need a lot of data. But not only do they need a lot of data, they need to be sort of trained in the right way to get us what we want. And we're going to talk about those 3 steps and how they get us what we want, the problem they're solving, and how they get us to where we want. So 3 steps are self-supervised learning, instruction tuning, and then reinforcement learning. Pretty much every LLM will go through these 3 phases of training, and each phase might have several steps, but these are the sort of high-level phases that we go through with different goals. So we start with self-supervised learning. So we're using very large plain text data sets, basically data scraped from the internet. It includes Reddit, it includes Twitter, it includes forums, it includes business web pages. The goal of self-supervised learning, and we'll talk about what that means and what self-supervised learning means in a second, but the goal of self-supervised learning, this first phase, is to learn those basic language skills. Which words follow other words? How do words relate to one another? How do you form a sentence, an English sentence or a Japanese sentence or a Chinese sentence or whatever? How do you form these sentences? What are these basic language skills? But if you recall back to how we trained models, when we trained a model, we needed a loss function, and a loss function needed a label. If we've just scraped all of this data from across the internet, just all these different undifferentiated just strings of characters of text, of books and words, and books were used illegally to train these as well. What we have there is we just have a sequence of words. What's the label that we would use to begin to do training? Because to do training, we need a loss function. We need to have a label. Well, what we do is we take those text, which we know exists, and then we just randomly pick a word from the sentence and mask it out. We say, all right, we're not going to give this word to the model. What we're going to do is we're going to ask the model to tell us what word it is. And so, in a sense, the data is self-labeled. We just take the data that's already there and we remove part of it, and then ask the model to predict what we removed. And this is a common pattern for training models in a self-supervised or unsupervised way, depending on how you want to talk about it. It's self-supervised because the labels have come directly from the data you're training on. You're not having to pay someone else to go and label all of the images. Imagine trying to pay someone to label all of the text in the world of all of the internet to try and get enough data. It wouldn't work. So we need to do this automatically. We need to have this system where we just know the answer already. So what we do is we just replace a word. So in this case, we have a model, and its job is repeat the word. It was a dark and stormy. And then when it sees mask, its job, and this is what it's actually being tested on, is when it sees mask, it needs to predict what word goes here. So if it predicts kitten, it was a dark and stormy kitten, obviously that's wrong. We can recognize that as wrong. There's some knowledge going on there. There's a certain set of words that would be good and a certain set of words that would be bad. And in this case, we don't actually even assess on all of the words that could be good. We know the answer. The answer is night. The answer is night. And if it doesn't say night, then it's going to be marked wrong and it's going to be told, okay, you should answer closer to night next time, and adjusts all of the parameters based on making it predict night better. And then you do that for millions, billions, trillions of sentences with words being masked out. And eventually, the model will learn, okay, what word goes here, what word goes there. And just implicitly in that process, it learns those word embeddings. It learns that night goes here. But also, because it might see other similar sentences with similar words, we don't have to tell it that night is similar to evening. It'll see the words night and evening being used in the same contexts, and thus will force night and evening to become similar embeddings. Okay, this is the first phase of training. And of course, if we do this, we do not have an LLM. We have a model that predicts a missing word. That's not enough. So what we have here is a model that can sort of continue on the sentence, right? It was a dark and stormy. What is it produces? It's the next word in the sentence and will continue that sentence. What that means, though, is that this model doesn't have any concept of multiple speakers. It doesn't have a concept of someone asking a question and the other side answering it. It just has text continuation, right? So if you ask it a question, it won't respond with the answer, right? So instruction tuning is the next phase, and this is where we start to teach it. It's build on those base language skills, and we start to teach the LLM how to take turns, how there's different identities in taking turns, and that one identity responds to the other. It is instructing, as in we are getting the model to instruct us, is one way to think of it, right? So in order to do instruction tuning, we do need to have manual labels. So what they've done is they've paid people to create data sets of instruction answer pairs. And this took millions of dollars that they spent to pay people to make these big data sets, hundreds of thousands of these examples, which is much smaller than the trillions of examples we scrape from the internet, but it's still a decent chunk of examples. And we basically getting a human to perform the task the LLM is supposed to do and showing it what it's supposed to do as an answer. And then we fine tune the LLM, just like we fine tuned ResNet on our image data. We're fine tuning what becomes an LLM, the model that predicts the next word. We fine tune it on this data using exactly the same process, right? We've got a loss function. Does it answer with the right words? And if it doesn't answer with the right words, we update the parameters. All of that's the same, right? And so this also has a very fixed answer, right? Somebody might have made a prompt, what is the capital of France? And then they wrote what the answer should be. It should be exactly the words, the capital of France is Paris. And if the model doesn't respond with exactly the words, the capital of France is Paris, then the model is marked wrong. And so instruction tuning essentially teaches the model almost a bit of a personality about the ways in which it's going to respond. It's not supposed to respond with just one word by default. It's going to be whatever pattern of responding was in this instruction tuning dataset. And these are proprietary datasets. So the OpenAI has theirs and Anthropic has theirs, which will be different. And it's part of why these LLMs sort of behave differently and speak differently, is because their instruction tuning is from different people with different ideas about how LLMs should be responding. But there's another problem here, and this is the last problem we need to solve, which is these answers that the model answers that this model is expected to be giving are very fixed. Like it can only express itself in these exact ways. It can only say these exact sentences. We would want it to be able to do something a bit more creative, a bit more generative than just copying from this data. Of course, this sets a baseline tone for how the LLM is going to respond, but we still want the LLM to be able to creatively come up with stuff and figure out how to say things better. So there's a question I see in the chat, are instruction test sets open source? There are definitely open source instruction tuning sets. Those exist, you can get those, but there are also proprietary ones. And there's a big mass and mess of training data sets for this purpose. Just the broad strokes is that the important ones that the big frontier companies use, they're proprietary. So the last step of training is to fix this last problem of it being locked into a certain way of speaking. Okay. And this is reinforcement learning. We want it to be able to learn by itself a bit more. We've got it pretty far. We've got it from being able to just understand language and be able to respond to requests, but the tone is a bit off at this point, and it's very rigid in the way that it is able to respond. We want it to explore and come up with its own way of being able to respond to questions, ideally even better than humans if we can, right? And so we use something called reinforcement learning. I told a bit of a fib before. I said that in order to train, you need a loss function, which means you need labels. There's a little more to it than just needing labels. You can do that in sort of come up with labels in a different way than blocking out text. What you can do is you can find some way to just tell the model directly yes or no. If you do it that way, you don't get to tell it how wrong or right it is. So a loss function tells you, you're wrong by 5%, you're wrong by 10%. But for reinforcement learning, all you can tell it is yes or no. Okay? But if you get humans in the loop here, you can get them doing that. You can tell the model, hey, that was a good response. Oh, that was a bad response. Right? That's a good response, that's a bad response. And you have humans in the loop and they tell them, right? Good response, bad response, good response, bad response. And for a while, that's all you do. You just get humans to look at it and say, yep, that's good. Yep, no, that's bad. And so sometimes when you're using these models, they'll ask you to do that for them. Do a bit of that, saying that's a good one, that's a bad one. Like giving that signal back. Of course, to be able to train an LLM, you can't just do humans in that. Like it takes too much manual labor to do that. We kind of want to be able to scale that a bit better. So there's another kind of evaluation that's done as well. Probably you do a bit of both. What you do is you train a second model. Train a second model to imitate the human evaluation. It doesn't need to know exactly how language works. It doesn't need to know how to produce a sentence. All it's doing is deciding, is that a good response? Is that a bad response? And turns out that if you do this, you can get a reasonably good estimate for it. And this is useful for training the other model. In some sense, that this is using like that good normal training to create a model to help with the reinforcement learning. Because reinforcement learning is pretty unstable because of the fact that you only tell it yes or no, you don't tell it how good or bad it is. You don't get to tell it how good it is, and you don't have that nice granular response. Reinforcement learning can be a bit unstable, and so you need to do a lot of it. And so this process where you have a model that imitates a human lets you get that done automatically and at scale. Okay. It's the end of the lecture. I said I'd go a little bit over. Hopefully that's okay. This is of course recorded. You can look at it later if you need to go. So let's summarize what we just talked about. Text needs to be converted into tokens through tokenization. This is a form of turning words into numbers so that the model can start to process. But more than just tokenization, we also need to turn those token IDs into embedding vectors. Those embedding vectors will encode similarity between words, or specifically between tokens, where similar tokens are near and dissimilar tokens are far away. And this makes those tokens easily processable by models. It makes it a lot easier for them to train, a lot easier for them to learn how to speak language. Is you already have these sub chunks of sub chunk of characters, which is a token, which have a meaning, which they know this word means kind of this already before it even starts. And then an LLM is a function which takes in a sequence of tokens and then uses all of those tokens to just predict one next token. And then we can write like a for loop over that to just run it multiple times in an auto-regressive manner to produce a whole output sequence. And the last bit was we talked about how LLM training generally sort of vaguely happens in 3 phases. Each one is trained slightly differently, but those are the 3 phases that are mostly used for training LLMs. All right. So let's now take I'm going to say 3-minute break because this is, we've got to come back and start with the next one pretty quickly. So 3-minute break, real quick, grab a drink, go to the toilet, whatever you need to do, and we'll meet back at 6:13, 6:14 actually, I guess. Yeah. And I will also get a drink back in a second. Gotta unmute myself. Okay, it's time to start up the second lecture of Module 4. So I'm going to start sharing my screen, and I hope you will be able to see it. We don't want that. All right. Hopefully you can see the screen, and I'm going to continue. Thank you, Roz.
Yep.
So this lecture, we're going to focus on multimodal generative AI and also a bit more on uh, producing those sequential outputs and some of the options we have when we do that. So actually, we're going to start with those advanced controls for the LLM outputs. We're going to take the process of generating generating an output sequence. We're going to make it a bit more complicated, and we'll show you why and how we can get some varied outputs from it. Because remember, if the model always takes the most common, the most likely, then it's going to be always giving you the same answer. And maybe we don't want that. And then we're going to talk about multimodal inputs. So if we have a model that can take in both text and images, well, how does that work? We've just talked about how LLMs take in text. How do they take in images? So we'll talk about that. And then we'll talk about multimodal outputs. This will be a bit more vague because it ends up being a bit more complicated. We'll discuss what it can do and what kinds of operations can happen there. So, at the end of this lecture, we want you to be able to explain how generation settings, so configuration settings, generation settings, whatever, and different prompting strategies can influence the LLM outputs, have an idea of what those settings are and what your strategies are. We're going to explain how multimodal AI systems specifically use a shared embedding space. We've talked about embedding space. Now we're going to talk about a shared embedding space in order to process and generate using different types of data. And then we're going to see how we can interact with multimodal generative AI systems to sort of generate different kinds of data and interpret different data types. So let's start with those advanced controls for LLM outputs, otherwise known as configuration options, otherwise known as parameters or runtime parameters. So let's recap again what an LLM is. An LLM is really just a function, just a box where you put in a sequence of words and out comes a probability distribution over over all the tokens about what is the most likely next token. And previously we just said we're gonna just gonna look at what is the most likely, and we're just gonna take that one. We remember that that's autoregressive, so we pick it, goes into the input sequence, and we run it again. And then that output goes into the input sequence, and we run it again. And so we can have this input sequence, and that produces an output sequence by sort of running the function multiple times, okay? So that should mean that we give the same prompt to the same LLM, we get the same response, right? We can test that out. So let's bring up two windows of ChatGPT, is what's currently on screen. And I'm going to ask them both to describe a dog in one sentence. So this is running ChatGPT, and this is running the same model, same prompt, same input. And what do we have? We have a dog is a loyal, intelligent mammal, often kept as a companion, known for its playful nature and strong bond with people. Okay, and then we have a dog is a loyal, intelligent mammal, is often kept as a companion. That's the same. And then working animal or family pet is kept as a companion, working animal or family pet. So a lot of it is the same, but later on it starts to vary. So if ChatGPT was to be doing the strategy of just taking the most common, like the most likely token and just responding with that, we wouldn't see these varied outputs, right? Can you think of like is that a good thing or a bad thing? Well, obviously OpenAI thinks it's a bad thing that we would always produce the same output. We can kind of think of this as like variety. Like how much variety do we get out of it? Obviously, we want some, otherwise it kind of is a bit boring, a bit doesn't it's not good. We would like to have options, um, but we don't want too much. So now we're going to talk about how we can get that variety, how we can get that randomness into text generation, right? So remember that LLMs produce a probability for each word or each token, whichever one you want to call it. We're going to use that probability as a probability. How do we use this to add variety to the model outputs? We use those probability per word, and then we choose the word based on the probability. So in this case, we would have a 44% chance of selecting the word hi, a 39% chance of selecting the word hello, and a 14% chance of selecting the word greetings. Okay. And if we do that at each step, we're going to be able to have varied outputs starting from the beginning, right? But you notice here that there's like a 1% chance of choosing the word happiness. Okay. Uh, why don't we see LLMs answering with nonsense answers, right? If it's random, we would kind of expect to see nonsense answers. And part of the explanation is it, part of the explanation is filtering, and part of the explanation is just that the model doesn't really give a high probability to the bad tokens, right? So we see here the 1% chance of happiness, of the word happiness coming up, because it wouldn't make sense to be the next word. So it's just not like very likely in the first place. But then we also do some extra filtering on top, and we're going to be talking about those settings in a few slides. Okay. So for starters, very few words are given reasonable probabilities. And when we're prompting, and then we have those other settings. And so when we're prompting an LLM with the word hi friend, there are a few plausible ways to respond, but none of them start with the word elephant or start with the word happiness, right? So it kind of looks like this. Let's talk through this diagram because I know it's a bit much. We're starting over on the left with the first output of the LLM given the prompt, explain why the sky is blue in one sentence. At the end of that, it gives this probability distribution with the word the with the most, and the word blue with the next, and then thanks is a very small probability. If we pick the word the, then it's going to run it again, and then we'll get this probability distribution. The blue, not very common. The sky, very likely. Okay. Then we got the sky that's now the input. We have the sky, and then we've got two different ones, and we have appears and is, and it's a bit closer, but appears is more likely. So we can sort of read this as the most likely outcome would be the sky appears blue because of Rayleigh scattering where whatever. And so the continuing token. So we have token 1, token 2, token 3, token 4, token 5, token 6. And you can see it sort of branches out of different possibilities, but we're always following, like we're always using the probability as a probability. We're saying, okay, there's a good chance, very, very high chance that it's the word the, but there's also a chance that it's blue. So if it was blue, then this is what it would look like. And so you have all these different words, all these different ways that it could respond, but each of them is taking like probable words as the next thing. And so as taking probable as the next word. So we can see that if we start branching this way, blue light from the sun is a completely different set of words to the sky appears blue because of. It's always this contextual thing, and it's always picking the right word for the current context. Right? So this sampling is done by normal computer code, right? It's not part of the model. The model doesn't need to model anything else. We've already modeled. We've modeled what are the most likely, what are the probabilities of all of the tokens. And so then we can just write a normal bit of computer code that's, everyone who knows how to write computer code would be able to do this. They can just go, yeah, we'll select these by the probability. What's important here is that we have these probabilities. And if we want to adjust how varied the outputs are, we can actually sort of fudge and adjust these probabilities after the model has already produced them. And we can adjust them with things called hyperparameters or configuration options, whatever you want to call them. There are 3 runtime hyperparameters for the next word selection, which we're going to talk about. We're going to talk about temperature, and we're going to talk about top P and top K. Temperature is a way to sort of push the probabilities in one way or the other, and top P and top K are ways to filter out words or tokens that we don't want to use based on them being not very likely. And it's really this top P and top K which really forces the model to never respond. If you say hi there, it'll never respond with the word elephant because we're filtering it out using top P and top K. But if we want to increase the variety, we also want to shove up the temperature a bit more so that it's more likely to pick other things. Because if we look at this one, you know, if we wanted blue to be the next word more commonly, we could use temperature to adjust that, and we'll see how that works now in the next slide. So if we put the temperature up, it's going to even out the probabilities. So the higher probability words become less likely because probabilities have to sum to 1. And the lower probability words become more likely. They get sort of bumped up and it's more likely to pick those lower probability. And that gives us output which is more varied overall. On the other hand, if we lower the temperature, it sort of accentuates the probabilities and makes the higher probability words even more likely and reduces the lower probability words even more. So a lower temperature is making the model more consistent. So if we look at that example, we can imagine 2 scenarios, one with a lower temperature and one with a higher temperature. So in the lower temperature, those most common ones, they're sort of emphasized. They're bigger probability. We're going to pick them much more often. These other options are small probabilities. But if we put a higher temperature, we're balancing out the probabilities more, and it's just more likely. At the start, we've got the is only a little bit more, or maybe 50% more likely to be picked than blue, where here it's like 9 out of 10 times it's going to pick the word the, whereas 3 out of 5 times it's going to pick the word the here. So the higher temperature makes the output more varied. So here's a little animation we've gotten from another place. You can see the link to it at the bottom. It sort of shows this really nicely. If you put a low temperature, you accentuate the probability. If you put a high temperature, you balance it out. So the cat slept on the, what's the next word? Mat is the most likely, so maybe we pick that. Temperature goes down, all the other probabilities go down. Temperature goes up, it all gets more balanced, and the probabilities are more likely to pick the other words. Now, as I said, we still don't want it to ever respond with the word elephant.
Sorry, Brendan.
Yes, Ranesh?
Right. The temperature, talking about temperature, but where do you control the temperature? Or can you explain a bit more about the temperature? Sorry, I'm lost.
Remember how I said that when we're sampling the LLM probability distribution, we're like choosing the next word, that's done in normal computer code. So in the same way that you might write a function that has multiple arguments, or you have a program that has multiple inputs, when you're running the code that runs the LLM, so you've got a program which runs the LLM as part of the program, but the other part of the program is like running the LLM in a for loop and sampling the words that are coming out. It's just a configuration of that program. It's just a number that somebody has typed in to say this is a configuration. In the same, what's another configuration? You know how you can name a file, and that's metadata about the file on your computer?
Yeah.
For when you're running the model, you can just type in a temperature, and that's metadata about running the model. You can just choose whatever value you like. You'll see it more in lab 8. Okay, you'll get to play around with this and you'll see it a bit better, but it really is just a number that you type in. It's 0.7 or it's 1.0 or 1.5, and it's just a number that you choose as a human when you're running the code. You get to choose it. It's a free choice.
Okay. Thank you.
No problem. All right, so as we were talking about before, if we prompt an LLM with the sentence, "Hi, friend," if we only use temperature, It kind of doesn't matter how we use temperature, the probability of every word is ever so slightly greater than zero. And so we will, if we don't do anything else, eventually, if we run it enough times, maybe it's 1 in 1,000 times, it's going to respond to the sentence, hi friend, with the word elephant. But in reality, we don't want that to ever happen, and it doesn't ever happen for ChatGPT or any of those models. So how do they make sure that it never responds to the elephant? They use top P and top K to filter that out as even being considered. Okay? And these are just two different ways to exclude very low probability words that we don't want to even consider as a possibility from consideration, while still allowing some variation of reasonable words. And often in practice, these are actually both used together. So top K is very easy to understand. It's just you pick an integer and you say, how many tokens will we ever consider? And so if you pick K of the top K being 40, you just say, whatever the 40 most likely tokens, those are the only ones we're going to consider. We're not going to consider any of the others. Then we're going to filter out all of the other tokens, all 200,000 other tokens. It's only the 40 most likely tokens that we're going to consider. It's pretty straightforward. It means that you get a very small set, you get a reasonably small set of words that you can ever pick that are probably going to be pretty good. And then there's another way, which is called top P, which is also called nuclear sampling, but you call it top P in the code and everything. And that's going to filter and restrict which tokens that can be selected by considering the total sum of probability which has been covered by the available tokens. This one is a little more complicated. It actually requires an algorithm to find out how many tokens you're filtering out. And you just sort your tokens by probability and you start including them. You start saying, okay, the most likely token, you include that one. And maybe that one, as we saw before, maybe it's high there and the response is hello, and the probability of hello is 41%. Well, that means that 41% of the total probability is already accounted for with just that one token. And then you consider the second most likely token, and you see how likely that is, and you include that in the list of things that you're going to consider. And then you've included more of the total probability, the total 100% probability is included. And so you set a threshold, usually around 0.8 or 0.9, where you want to cover a lot of the mass of the probability. Like you want to cover a lot of the likely options. You don't want to have this extremely long tail where you have hundreds of examples with 0.001% chance of being picked. You just sort of cut them off by setting these. And when you set these together, you can control the outputs in nice ways, and you'll get some experience with this in the lab, seeing how these work, and you'll be able to play around with them. Another thing you can technically do, but it's just mostly for evaluation test purposes, is that you can set what's called set the seed of randomness. So computers, they're actually pseudo-random. They don't technically produce random numbers. They produce numbers that look random, but not actually random, because that's how computers work. They are deterministic. The same inputs give the same outputs. So what it actually uses like the clock of the system and then puts that into like a complex mathematical function, which produces a number that seeds your random generation, random selection. You can technically set the seed, and then if you manually set the seed, it'll always give you the same answer as if it's like the same random choices were always being made. And you're sort of defining a universe in which that always happened by setting a seed. And if you change a seed, you're changing a universe where different options happened. This is, like I said, this is mostly used for test purposes to make sure that you get the same output. If you change code or something, you change which model, you want to see, does it give the same output? You can also set the temperature to 0, which ends up with the same idea where you have always the same um, always the same sequence coming out. You never have any differences. But that's a different idea because setting temperature to 0 means that you're only ever picking the most likely token. But if you set the seed, you're only setting you're setting which choices the model made. You're setting up a universe in which the model has made exactly the same choices because it always works deterministically. It's a little complicated. It's not super important, but it's good to know that you can do this. Next, we're going to talk about those are hyperparameters you can choose. And before we talk about the next hyperparameters, we sort of have to take a step back and consider something that we haven't talked about, which is sort of more practical, which is when you're deploying an LLM, there are some practical compute limitations. Because LLMs, they require a huge amount of computing time and memory, as you've seen in the labs. It takes some time to get some answers out. And modern LLMs, they use over a terabyte of GPU memory, and maybe they have thousands of tokens in their context history. What vendors are basically selling you with the chat-based web-based chat interface, not yeah, web-based chat interface. What they're really selling you is just sort of brief access to like hundreds of GPUs to quickly process your query and then get your answer, and then that's what they're giving you. And so when you pay for it, you're paying for more of that time of the GPU, more of the electricity and the time of the GPU RAM. But interestingly, it's actually the memory requirement that stops you running it locally, not really the electricity requirement. If you wanted to run these locally, the amount you pay to the companies is a little bit more than you would pay if you owned enough hardware and just ran your own stuff using your own electricity. Like paying for the electricity to run it would be cheaper than paying them to use their electricity to run theirs, right? So the main thing that we care about is memory costs. And so we have some hyperparameters we might consider to control the memory usage, right? This is a consideration when if you're deciding you want to run your own LLM on premises at your business, then you'll need to consider what hardware you would need to run that, and then the cost of running that hardware, like the electricity costs of doing that, and you have a couple different things you want to tweak. To control the memory usage, which is you've got certain hardware has certain memory amounts, so you need to be able to control how much memory it uses. One of the things you can do to control how much memory that could be used is to control the context window size, and that'll control how much memory it uses up. And then the cost of running that hardware is going to be like how long can it run for any request. You might want to set a maximum number of output tokens. So remember we talked about the context size, how if a model has a context size of 4, then it can only see the last 4 words, last 4 tokens, and it can't see anything else. In reality, a small context window is something that's less than 100,000 tokens. So around 100,000 tokens is still a medium small size context window. As this context window gets bigger, you have to hold on to more computation before you can get to your answer. So a large context window starts using more memory. But a weird thing about this is actually that for the small context windows, because of how big the models are, the majority of the RAM usage is still actually just the weights. It's still the weights of the model rather than this extra computation for the context. But when you get to more than 1 million tokens in context, usually the context itself becomes about half of your memory burden, the memory amount that you need to hold on to in order to run these. So you choosing the context window size is another hyperparameter that you can consider if you want to deploy these things locally. The other thing is the maximum output tokens. Remember that each generated token requires a full pass through the LLM. We can do some caching, but it still ends up being reasonably costly. So it takes time and electricity to do that. Sometimes, usually, there can be degenerate cases where the model starts producing a lot of text and then you want to stop it, prevent it from that ever happening. You will set a maximum number of output tokens, and all of the LLM providers will have some maximum output tokens set for them to sort of control this. And this, we know that output tokens are expensive because LLM providers, they charge you based on the number of output tokens. You get like a number of credits, which are equivalent to a number of output tokens. and input tokens, but it's like the number of tokens is the issue, right? So those are the sort of free choice hyperparameters that can control LLM outputs. Now we're going to shift gears a little bit and talk about prompting, because that's also another way that you can control the outputs of an LLM. And we've talked about this before, but we're going to talk about it again now that we've got more knowledge about how LLMs work. And we'll talk about system prompts and user prompts. Remember that a system prompt is something that sets the overall LLM behavior. It is usually written by a developer. So the AI vendors, when you go to the chat window, they have a system prompt that they've written, but you don't see. They've written the system prompt, tell it how to behave, tell it how it should respond to you. And that system prompt that they've written they write it once and then it's applied to every conversation, and it's just part of the conversation context that the model has seen the system prompt telling it what to do. That's different to user prompts. That's what you type in when you go to the web interface. You type in a thing, that's your specific prompt, and that's going to change every time you write a prompt. That's the variation. So the important difference here is that system prompt is written by a developer. So if you're going to make your own AI system, you're probably going to be writing a system prompt telling it how to interact with users, right? So for your third assessment, you're probably going to be thinking about system prompts. So now that we know a bit more about models and we know that LLMs, all they do is take in a sequence of tokens and predict the next tokens. They can do so much with that, but at a mechanical level, all that it's doing is just a sequence of input tokens with predicting the next token. So how do those system prompts and user prompts and control tokens all fit together? Well, remember we talked about those control tokens and how they signified taking turns, about how it say that this is what I said, this is what you said. There's also control tokens for system prompt. And so if we look at our example again of what you see in your ChatGPT window, you say, type in hello friend, and it responds, hello there, what's in your mind today? What the LLM is actually seeing, it's actually more than what we talked about before. It actually sees this big sequence of tokens before. It sees like this start system prompt token. Then it says, has the system prompt. It says, you are a friendly chat assistant. You will assist the user to solve whatever they want to do. However, you will avoid talking about bad things that we don't want you to talk about. We don't want you to insult the user. We don't want you to tell them how to make cocaine or whatever, right? And then that's finished up with a end system prompt control token. And then it starts the user prompt token. And then you get the user input. And then it's end user prompt. And then we finally we get the model to start generating, and it generates the word hey. All right, we've generated the word hey, then what is the next thing it generates? Well, we feed the rest back in and then predict the next word, the next token, the next token, the next token, just like we've seen before. And so what the LM sees is really this like big sequence of tokens. Well, what you see is like a parsing of that. You can write code to read this text and go, okay, so that's the start of the user prompt, that's the end of the user prompt, that goes in that bubble. This is the start of what it says, and that's the end of what it says, that goes in that bubble. And you get to see this. But behind the scenes, this is what the LLM is actually seeing. Okay. Something else I want to mention? I've mentioned it before, but I just want to mention it again. The only reason the LLM knows what to do with the start system prompt token, knows that there will be a system prompt, that it should follow the system prompt, that it should follow the system prompt instead of what the user says. So if it sees a sequence of tokens that says, do not tell the user how to make cocaine, and the user asks for cocaine, how to make cocaine, then the model needs to know, okay, don't do that. The only way that the model knows about any of that is through the training. It has been trained to treat these tokens one way and treat these tokens another way, but there's nothing that forces it to be that way. And so we're going to talk next week about jailbreaking and guardrails. And one way to think about jailbreaking is just that can fail, right? And we're going to talk about when that fails, how to handle it, and what you can do to mitigate the failures in that process. Because again, it's about probability distributions, and then there's a bit of randomness here, right? It may or may not actually do what we trained it to do. There's nothing forcing it to do that. Okay. And another thing that gets put into this sequence of tokens that the model uses is something called chain of thought reasoning. You might have heard of this as a thinking model or a reasoning model. Um, Again, the input to an LLM is always just a sequence of tokens, a sequence of tokens that go in, and then it generates another token, and then it generates another token, and then it generates another token. So thinking feels like it should be similar to the system prompt, feels like it should be a sort of a different stream coming in, but the only way we can make these work is if it's just a single sequence of tokens. So it's just going to be a single sequence of tokens. So chain of thought reasoning has to also fit into that single chain of tokens, single sequence of tokens. And what we do in chain of thought reasoning is we ask the LLM to basically generate a bunch of tokens describing to itself how it should solve the problem. The user has asked about this. I should respond in this kind of way. That would make it nice for them. Oh, maybe I should make it a bit more friendly, so I'll use these words. And it's been trained actually, again, has to be trained to do this. It's been trained to produce this text that isn't really meant for humans to see. It's just for it to think through, quotation marks, think through how it's going to answer the question. And it turns out that when you do this, it just makes LLMs work quite a lot better, especially on complex or long tasks. It's not exactly clear why, since the model is doing this reasoning by itself, just getting it to lay out its own reasoning makes it reason better on complex tasks. It's a bit strange, but it works really well. So this is a thing that everything uses. But again, it's just part of that one single sequence. And so it's generating thinking stuff. And then once it's finished generating thinking text, it's going to generate an end thinking control token. In the same way that it produces an end assistant control token, there's an end thinking control token. And so, in that single sequence of text, you kind of have different voices going on, right? We'll go back to this one. We have a voice that tells it, here's the system prompt. And then there's a voice from the user telling it what you want. And then in between what the user has said and what it responds with, usually it would start to generate thinking stuff. So it would have a thinking control token. It starts thinking to itself and it has a voice to itself saying, I should do this, I should do that. And then it ends that with the end thinking control token, and then it starts talking to the user, and it uses the voice of being a friendly chat assistant, and it's doing what it's being told to do, and has the voice of a friendly assistant. But that's all in the same sequence of tokens, and a lot of the way that it appears the way that we see it is based on the surrounding code treating it in that way. Okay. So that takes us to the end of the sort of controlling how an LLM can produce outputs, even though it is just sequence in, token out, sequence in, token out. Now we're going to talk about multimodal inputs. So there's a question in the chat. In assessments, did we use a system prompt? No, in the assessments, you were only doing user prompts. You will be looking at system prompts in the coming labs. It's not that different. It's just a matter of like authority and telling it the kinds of tasks it should do. All right, so multimodal inputs. Now, we've just talked about how LLMs can process text, but of course, our world is much more than just words on a page. We experience the world through, like a lot of us use vision to understand the world. We use audio to understand the world. We see moving pictures to understand the world. And if everything we just talked about was getting text into an LLM, we'd like for an LLM to be able to understand images and audio and video. So now we're going to talk about how can an LLM handle multiple modalities of data? Is it images, audio, and video, and text? Those are different modalities of data. Text is a modality, image is a modality, audio is a modality. And so multimodal just means more than one of these is being used at the input. So again, hammering it as much as I can, LLMs only understand sequences of tokens. However, images, audio, they're not exactly sequences of tokens, are they? An image, how's that a sequence of tokens? That's not a sequence of tokens. Audio, maybe you could say each like loudness level is a token, but that's too many tokens. That would be because remember, we can't have too many tokens, otherwise it takes up too much RAM. And this is like 40,000 samples per second. Too many tokens. It's not really what we need for tokens. So how is it an LLM could handle them? Well, actually, it's kind of a simple, easy, maybe even dumb way of doing it. We just want to convert them into a sequence of tokens. We just need another model that can take that input and turn it into a sequence of tokens. Sorry, I've muted you, Mira. If I'm talking in unmute.
Sorry.
So we need another model that can turn this image into a sequence of tokens. And if we just have an image model to do that, we're kind of good. We can feed that into tokens that the model can understand. This isn't actually all that strange, to be honest. It's already fairly similar to how an image model works. An image model takes in that image, and then from that image, it produces like a vector of visual features. That's just a normal thing that image models already do. They produce a vector of the high-level features, right? Sort of conceptually, those high-level features of images are also kind of similar to word embeddings, right? Is there a dog in this image? Is there a person in this image? Those are words and concepts. Like words are concepts. And so high-level features are concepts. There's this sort of overlap there. So technically, we need to make sure that we train an image model alongside the LLM so that they speak the same language, basically. But the basic idea aligns really well already, right? We have those high-level features that an image model already produces. That's something that we know they can do. And then we sort of train it to produce features that are similar to the words. And we'll look at that in a moment. But not just that. It doesn't make sense to describe an image as a single word. So instead, we're going to turn one image into multiple tokens. To do this, all we do is we cut up the input image into those tokens and then feed those cut up pieces of the image independently into the model to produce the output. And so that looks something like this. So we might ask this LLM, what is in this image? And each of those words are tokens. Those go in. And then we start giving it image tokens. And each image token, the first one is just like a one token for the whole image to start with. And then we take these patches from the image and we start feeding those through. And so we have, what does the overall image look like? And then here's another part of the image, another part of the image, another part of the image, another part of the image. And we get these embeddings of these parts of the image which can go into the large language model. Okay. That's reasonably easy. We're going to talk in a moment about, very soon, about some consequences of this, but I just want to quickly mention that audio is the same idea. Instead of taking each loudness thing, you break it into chunks And then each chunk goes through an audio model and produces a sequence of tokens that gets fed to the LLM. And it can be the same. However, I will note there is sort of a shortcut you can do. Is a different way to do it is you could use a dictation model that takes if the audio is just human speech, right? If it's just you want to get words out, well, you could use a dictation model to turn the audio of speech into words, and then you don't have to worry about it. You don't have to do anything else. Because remember, this image model has to be trained alongside this language model, which adds complexity to the training. You have to be able to have images alongside of text to do training. So that adds a bit of extra complexity. For audio, if it's just speech, it's probably easier to just do a dictation model and then just use the text that comes out, put that into an LLM. Okay. So whether it's images or audio, the input to the LLM has to be a embedding, has to be a single vector, which is an embedding, which kind of just means by default that those image chunks or audio chunks have meaning inside of that embedding space. Remember that inside of an embedding space, similar points mean similar things, and dissimilar points mean dissimilar points are sorry, let's say that again. Similar ideas are placed close together in the space. Dissimilar ideas are placed far away in the space. So just by default, in order for this to work, and we know that it does work, and we've sort of seen how it can work, these image and audio chunks have to be placed into that space and satisfy these conditions. And so we can end up with something that looks a bit like this. We might have our learn space for words, but then when we encode or embed this word chunk, it's going to be placed into that space. And when it's placed into that space, like I said, it kind of has to, for the model to work, be placing that in a spot that makes sense to the model, that puts it in a similar place to words that mean something similar. So this little patch here, maybe it would be placed somewhere between dog and wall, the words, and far away from the word golf. Of course, in practice, it's a bit less clear, but this is the theory. This is how we hope it will work. When you have a model that can take in both words and images and has that shared embedding space for them, we call that a vision language model. So a vision language model basically consists, saying it again, vision language model consists of an LLM and some kind of image model, either a CNN or a transformer. You can have different kinds of image model. So what do we use what can we use vision language models for? Well, they're really good at being able to explain images in words. So the obvious thing we can use them for is for visually impaired people. People who can't quite see what it is, it can describe them to them. You can do screen readers, you can do describing what's in an image, you can describe anything. You can describe video with this, right? And that'll be useful for them. Also can be used for detecting manufacturing faults. And what's cool about a vision language model, as opposed to just a classification model, is that you can describe in English what faults it needs to look for. You can say, all right, you're looking for this kind of fault, and here's what it looks like. And you can use the same vision language model that somebody else uses for theirs. You don't need to do anything else with it, and you could use them in that zero-shot manner. Of course, maybe it works good, maybe it works well, maybe it doesn't work well. You'll have to test it out yourself. The alternative for that would be like training a CNN, or training a vision model by itself to classify, is this a fault or is this not a fault? But when you do that, you lose some of the flexibility even on the output side. You lose the flexibility of getting it to even describe why it's a fault, which could be useful, right? If you could get it to say, okay, this is a fault, it's a fault because this will cause stress, or this looks like it's this kind of fault, but it's got a bit of this other fault, right? All classification is a bit not quite right anyway, so it's good to have this flexibility there. Another use is you can extract text from images with the optical character recognition, and you can sort of guide it with instructions. So that's multimodal inputs. That is, there's text and images coming to the input. Just really briefly, because it's kind of too complicated to get into exactly how it works, we're going to talk about multimodal outputs, which is a different beast. We're going to talk about using one mode input, another mode output. The most common of these is of course generators. So image generators, audio generators, where you give it a text prompt and it produces an image output, right? Multimodal, text in one mode, image out another mode. So when we're using the multimodal inputs, we have that shared embedding space where the text and the image share a meaning. Well, that same idea can be used for image generation and audio generation, right? You can think of the multimodal inputs as teaching the image model how to speak the language of the LLM. For multimodal outputs, you can think of it as teaching the LLM how to speak the language of images or audio. It looks kind of like this. This is, like I said, it's more complicated, as in there's more variations and more steps going on than the other way around, but it's still, this idea holds. You put your text into a large language model. Your large language model produces one or more output tokens. Those one or more output tokens get put into an image model, and that image model learns how to take these tokens and produce an image. Now, one thing you might not recognize at first when you see this is that this way is actually a bit harder than the other way around. So converting an image to a word, you lose information. You lose a lot of detail. These are all dogs, but they're all very different kinds of dog. They all have a bunch of extra different information about it. Where is the dog? How big is the dog? What color fur does the dog have? All of that stuff, that is the information which is lost when you're going from image to text. So if you want to go the other way around, you want to go from text to image, you need to do something else. You need to do something extra. You can't just say, all right, give me a picture of a dog, and this one word, dog, would always, if you don't do anything extra, it would just be this one word dog can only be this kind of dog. Right? So you need to add something to make it have this variation. And the way you do that maybe seems a bit dumb. You just add randomness. You add a random vector alongside it. So you go dog plus random, and the model treats the random as all of those extra bits of information. How big is the dog? What color is the fur? That's all randomly chosen by that random vector. And so when we looked here, and the stuff's coming out from the large language model as embeddings, at each of these spots, it's what's coming out of the large language model, and it's a random vector. And then that sort of guides it to be able to come up with the rest of that information that it needs to sort of have this variation going on. Okay. And that's fundamental to all image generators and audio generators. And the last thing we're going to do is really quickly just go through a sort of slideshow, nice, relaxed at the end, slideshow of different image generation tasks that have been considered that, oh, hold on, that just disappeared. Let's present that again. Okay, whatever. A bunch of tasks for image generation. If we can go through, no, it's not letting me. Okay, we're just going to have a look at it this way. So we have in painting and out painting, where in painting is you sort of block out a part of the image and you say, all right, fill it in with something new. And you can tell it with language as well, what you want it to fill in, with a vision language model but with image as the output. You can do outpainting, where you can take an image and you can say, all right, expand that image with plausible parts outside it. And you can do that. Those are fun. You can do style transfer. You can say, all right, take this image and imagine if Monet painted it. It's a common one. You can move characters from one picture to another and So we could do this, where we say place the first two dogs, the dogs in the first image into the third image, and we'll do something like this. You notice that it does, in this case, completely remake the image, so it has some other changes to it than just like placing the dogs in there. And the last one we're going to talk about is super resolution. This is just taking a blurry image and making it less blurry. All right. So you can also produce audio. We're not going to really talk about it. It's very similar, except of course audio is sequential, just like text is sequential. So it's auto-regressive, and it will produce tokens and then produce some audio, and then based on that audio, produce the next chunk of audio, and then produce the next chunk of audio. But it's the same idea. So in summary, we have temperature, top K, and top P to influence the responses from the LLM. Those are the hyperparameters. They change the probabilities of the tokens which get sampled for each step of the LLM. And you can tweak these at runtime. You don't need to have trained it to do this. You just use these at runtime to change how it works to get a more varied outputs by setting these ones. The other thing to consider is LLMs use control tokens, and they use control tokens specifically to distinguish between system prompts and user prompts, and between chain of thought reasoning and user prompts. And there's these different voices that all get mixed together in one single sequence, but are indicated by control tokens. And the third key concept is we use shared embedding spaces to enable multimodal AI, where we put images into the space of words, or we put words into the space of images, so that, again, in a shared embedding space, similar ideas are close together, dissimilar ideas are far apart. Okay, I've gone a little bit over. I apologize. That is it for these two lectures. There was a lot in them. I hope it all makes sense. And I'll see whoever's coming to the lab when I see you. Oh, before you go, I have a little bit of an announcement. This week's lab, we only have one lab sheet. It should be reasonably easy. We have deliberately done this so that you have a bit more time to work on assessment 2. Assessment 2 is, of course, due Sunday. And the last announcement is that on Friday, I actually won't be taking the labs. I've got something that's come up I need to go do. And so there'll be someone else taking the labs on Friday. A colleague of mine, Aaron Harris, will be taking them, and he'll be able to answer any questions. He's very good. He'll be able to answer your questions about assessments and about the labs. He'll be fine. All right. We now need to swap over to running out of tardiness tokens. I am running out of tardiness tokens. I am. We will now swap over to the lab. So if you have any questions about any of the lecture, you can bring it to the lab session, but we do need to go to the lab session. So thanks everyone. Thanks for coming. Thanks for paying attention, and I'll see you guys in the labs.
Thank you.
Or next week.
Thank